So again, good afternoon from my side and good evening for people watching us from Europe. My name is Mihai Nica. I'm head of reliability and cyber physical system here at AVL at the headquarters. I will try to talk for the next 30 to 40 minutes about AVL vision on automation of test cases, especially on the ADAS area. So generating test cases is not something it's not a new challenge, let's call it like this. I mean, it's known in the software development since, or it's researched in the software development area since a long time. However, it becomes crucial, I would say, and we see also a lot of movement from other companies when we speak about autonomous driving systems, so ADAS or AD, fully autonomous driving systems. Before I start, I would like to give some background information about AVL. I'm not sure how good it's known in this community, so I will share some information with you. AVL is actually the largest privately owned company in the world. It's not very known as Porsche or Continental. However, in the year of 2019 was #1 engineering company in the world. So not just privately owned, but in the world, because we had huge business figures explicitly in the engineering area. It was founded in 1948 with a Marshall US plan. So it's US also behind the foundation of AVL. Back then we worked when we started with testbed engines, the old Professor List, and the founder of the company. We are now about 11 to 12,000 employees, depending on the year. And it's investing more than 12% in their turnover. We had a lot of patents. I think we are the company which has the most patents in the area of powertrain engineering. And our customers are about 97% outside Austria. So we are actually exporting most of our products externally. We are globally present everywhere, very strong presence, of course, in Europe, in Germany, in France, in Austria, where the headquarters are, but also in Sweden and in Eastern Europe, also very strongly developing a lot of our software capabilities, but also in North America, a strong presence, but also in Asia, in China, in Japan. We have really good customer relationships and good customer networks. So as I said, more than 40 countries where we are either developing or working directly with customers on site to bring different engineering products on the market. The company is structured into 3 large business units. One business unit where I'm coming from is the engineering services, about 40% of the total of business figures. Here we are focusing mostly on, and the name says, providing of engineering. So there is no dedicated product, no software tool or test system, but really developing from system engineering up to software development, up to SOP, and this is then delivered to the customer and he's doing production. Then the second largest one, about 45% or 43, 44% of our business is developing of test systems. So we are always competing on player #1 in the world with other competitor. I will not say the name now. So we are providing test systems from powertrain test systems up to engine test systems, up to full vehicle test system, everything from virtual test systems up to hill and vehicle in the loop, and even proving grounds all over the world. And there is a third division which makes about 5 to 6% out of AVL, which is the simulation technologies. This division deals mostly with providing tools for simulation. So these are the tools which the other 2 divisions are using, but also licensing to some extent. Okay, that was shortly about AVL. Actually, I was invited to speak about ADAS AD testing at AVL. So I will try to give a perspective of that. My department is strongly in the generation part of this particular area. I will not focus very much on the physical capabilities and so on. I think that's not something of interest for this audience. Give a short overview, but try to provide you what we use, the state of the art. The methods I will short present during this presentation are also patented, so we are quite on the edge on that. And as far as I know, or as far as we know, there is nothing similar right now available on the market. Before we go into that, what's really important is that to understand that the whole ADAS and autonomous driving storyline, it's just one part of the story. It's electrification, it's mobility, it's data intelligence. All these pieces of the puzzles make what we call autonomous ADAS level. So this is this self-driving car we've seen in Tesla or Google and so on. So AVL looks at all these four technologies. So it's not just ADAS and autonomous driving, but we look at all these four technologies and we combine them to provide these solutions for ADAS and for developing such kind of systems and test systems. Again, I'm not sure to which extent this is known, but when we speak about ADAS, IADAS or AD, these are the two keywords we usually hear about. So it's one, it's assisted autonomous driving. The other one, it's autonomous driving. So less assistance, more into autonomy. There were a classification of levels, starting with level 0, which implies actually no autonomy, no functionality, carrying on with level 1, where you have the adaptive cruise control, but there is no steering, no active steering from that. Going up to level 2, where there is some steering, like for example, the famous autopilot from Tesla, that's a level 2 functionality. Moving towards level 3, which is more of for the human driver, there is no difference. So there is no big difference between level 2 and 3. However, for the systems, there is an environmental awareness. So far, the only company which managed to bring this was Audi with the A8. In Europe, it's certified level 3. In US, due to the changes in the regulation, there is no level 3 for the moment. And also the ones which are delivered, the Audis which are delivered to Europe, they do not have this. And one example of Audi is the jam assist pilot, the traffic jam chauffeur, which works quite good. We also tested it here in Graz, and it's quite an excellent level 3 functionality. The next levels 4 and 5 care less about the driver. So the difference between level 4 and 5 is that level 4 is fully autonomous, but only for special situations. It's called geofencing. So there is like a special portion in of a highway. US, for example, has more than 150 highways which are level 4 confirmed. So a Tesla or a Ford, these are the only cars so far which can do this, can autonomously drive for those highways. So that it's available. And in level 5, you do not have this restriction. So in level 5, there is absolutely no restriction. The driver is not needed anymore. But why do you do this? So there are three important, from our perspective, there are three important aspects for doing autonomous driving. Of course, the most famous one, accidents. So we want to reduce accidents. And it's very, very interesting. And I think it's mostly known that a lot of the accidents which happen, 94% according to some statistics, could have been avoided because it were human errors inside. There was no technical failure. There was no tire exploding or transmission blocking, but there was really an human either overspeeding or ignoring signs or ignoring priority rules or alcohol, of course. And that's the biggest motivation behind trying to put ADAS and AD into that particular into the car. Autonomy, what does it mean? So we have people which cannot drive, we have drunk people, of course, and we have underage people. So being able to provide a car, and it seems very futuristic, but I think we are not so far away. But so being able to provide these taxis, at least to some extent, in certain areas, provides autonomy for different category of people and different stakeholders. And another thing is traffic congestion. So on one side, so there is this traffic assist jam. That's an example from Audi, but there is also the example where you would have a robotaxi or a level 5 or a level 4, where you can use time to do something else, read some reports, read some emails, react to things, but also be able to plan traffic. So that's also one aspect which improves, and this also has a CO2 footprint for most of us. So trying to reduce traffic congestions by proper traffic planning by using autonomous levels. This sounds very, very nicely, but the question is, when do we have all this? So we have Elon Musk, which says 2019, by the end of 2020, we'll have 1 million of Tesla robotaxis. Well, we are now almost end of 2021, we are not there. So I think that was an overestimation. We have more conservative people like Toyota, where they say we are so far away from everything which level 5 means. 2017 is not so far away as a statement, but still, I think he's also overestimating. And there is also the CEO of Argo AI, which is a spin-off financed by VW and by Ford. Actually, a lot of the software comes from that particular spin-off. He says, I think on the Verge, he had an interview and he said, the driving cars will be there when we and they are ready. So there is, of course, an interesting statement. What does this mean? There is a lot of philosophy. We should skip levels. We should not do level 1, 2. We should skip directly to 4 and 5 and so on and so forth. The reality is, for us as a company, and we worked with almost all premium OEMs in the world, it's you cannot skip the levels because you learn a lot of the levels. You do a lot of mistakes, but you learn a lot of these mistakes. So it's exactly when you brought the first vehicles, there was a lot of accidents with the first mechanical vehicles, and now we have very safe vehicles and very, very, very trustworthy vehicles on the streets. So it's a journey we have to do, and we'll have to see when this is ready. But my estimation would be that 5 to 10 years, we'll see a lot of level 3 to 4 for functionalities. What does this mean for AVL? So on one side, of course, it means providing engineering services with that respect. And this is where we as a company work very strongly in the ADAS area. On the one side, it's the system and calibration, and then the testing services. So where I will also go more into detail. And on the other side, it's control development for us. So providing these kind of solutions. And there is, of course, a part of providing tools and infrastructures. I will not go too much into that details. And all these have to be provided all over the development phases. So you have to move to the whole V model, but you have to have a different way of approaching the DV model, a little bit of a more agile approach. We have on the air updates, there is another life cycle behind it. There is another timeline. How Tesla is doing properly updates. Tesla is collecting data from all the vehicles, learning new things, updating the other things. So there is a very huge dynamic, which is now being brought in by the ADAS systems and has to be addressed in the challenges. But what is the motivation? Why do I need to test so much? Why do I want to talk to you about test automation? So on one side, bringing ADAS AD on public roads, you need to prove that you covered things. If we speak with customers, if we speak to somebody, he will ask us, how can you prove us that you test all the variations? Of course, it's almost an impossible question, but there are ways of answering this, and I will go more into details. There is a classical approach of driving the car around for miles and miles and miles, which is a classical, we call it fleet validation or SOP validation. You had 120, 130 vehicles, 150,000 kilometers, 1 year collecting data. That was an excellent approach for software calibration and durability. However, ADAS AD testing means testing 250 million of kilometers, and nobody can do it on the street. There is no possibility, not even Google. Try to do some corner case and try to do some smart testing. That would be a good alternative, but you have to prove that you cover the domain. That's very important. There are standards requiring this, and this is a challenge behind it. We offer, and I will also present in this presentation, methods which go exactly into this area. Try to prove that we covered situations which are necessary to be covered, and also give a feeling of metrics. So what all these 4 points means, it means we have two big challenges on the ADAS. On one side is being safe and secure. So you have the ISO 26262, which is dealing with intrinsic safety. So basically how the vehicle it's safe as a system. But you also have the SOTIF standard, which is dealing with extrinsic safety. So addressing all these situations, all these corner cases, edge cases, so everything which is critical. And you have another challenge, which is a cybersecurity. So you have the on-purpose attacks. How can I test all this stuff? And then you have the complexity. You know, there is a famous video of a lady in an old chair chasing an electrical chair chasing a duck on the street, which is Google presenting us this video. So having complexity of scenarios and managing this complexity of scenario, this is the challenge, and these are the points we are addressing. You have further on technology challenges. So you have corner cases, as we discussed about, but you also have AI algorithms. You have a lot of machine learning, and you have a perception system which might be reliable or not be reliable, which might be aging. You might have problems with the sensors, with the whole fusion. And you have also, of course, a major thing which is connected to the system verification as a whole, integrating everything, AI, perception, and everything, generating the proper corner cases and verify it as a whole. Where are the technologies? So what we actually do is trying to, when we set up the framework and then also a method behind that framework, which covers everything starting with the mill simulation up to road testing. And what we basically try to do is to look at everything we have as available information. So we are part of several, also with TNO, but also in other groups. We are also very strongly present in the ASAM groups, which are responsible for standardization. So we try to get regulatory on one side, we know the engineering, we get the real world data, which we get from crash database, but also from other sides. Try to manage this know-how, and also additionally we develop what we call an ontology, a knowledge-based model, and then use all this to structure the information and generate test cases out of this information, which are not redundant and also very efficient. So we try to cover as much as possible with one test case, and then start doing execution of those test cases in different environments. Most of the test cases will happen in simulation. Then when we learn about simulation, what's critical, what's not critical, we filter and we run further test cases in hill, mill, and so on, up to vehicle and road testing, where we have the least amount of testing. Why do we do this? Well, because the SOTIF standard gives us this picture. What does this picture means? I'm not sure if you can see my problem. You cannot see my mouse. Let's see. Yeah. Just a second. I will try to activate the laser. Can you see my mouse? Yes. So the SOTIF standard gives us this nice picture here. They say using standard fleet monitoring, fleet testing, random testing, which is also loved by Google, fast testing, you get a very limited test coverage. And the biggest challenge right now, so it's not about covering the whole world, but at least to cover the parameter stage, is to try to move this small circle here towards this big circle here. So, and try to detect they are dividing into 4 areas. There is known safe and known unsafe, unknown unsafe, and unknown safe. And of course, you don't just want to see unsafe things, but there are also things which are very interesting, which are safe, but might be annoying, like a vehicle sitting in a traffic jam and not being able to move because it was poorly calibrated. So you have to see this unknown, to extend your unknown area such that you cover as much as possible. And you have to prove that you have this coverage against the parameters. So what we propose is, on one side, use a knowledge-based representation, an ontology representation, combined with the generation method, which has in the background an adaptation of constraint programming and combinatorial testing to generate test cases, avoid any redundancies in that generation. But this generation is based on parameters. You will see it later on what I mean by parameters, which are in relationship to the SOTIF standards. Create this set of test cases using our algorithms, execute the test cases in different environments versus simulation, and then moving towards upper levels of execution, perform analysis of the results, and of course, based on analysis, you can repeat this process. We try to cover all the potential use pages of that particular functionality. If we do an autonomous emergency braking system, we focus on that, and we to avoid any redundancy, and we look at covering parameters all over the ODD, the operational design domain. Like, for example, this lane. So you have different colors, different number of lanes, and so on. The second approach is, after trying to do an exhaustive approach, parameter-based, combinatorial testing-based, we apply what we call the game-based approach. So we play against the system, trying to see if we can find any more crashes after testing exhaustively. What does this mean? That my system, my environment wins if we manage to find a crash when performing against the system under test. It might the ADAS AD functionality. With these 2 methods, we manage, at least with respect to parameters, to extend to a full test coverage. And we have papers published here. I will not go into much detail, but we managed to create this extension, which the SOTIF also requires. I will now go shortly to the to the methods, particularities. So the first thing about this ontology-based test case generation is to create an ontology which is a representation of the world as we understand it. So on one side, we have two parts of it. One static part, which describes all possible traffic signs, weather conditions, road conditions, lane types, and so on. It's always market specific. So we have an ontology for Japanese market or for Chinese market looks different than the one in US, and even then in US looks different than the one in Europe. And even in Europe, we have difference because there are different kind of signs, but everything is here in a very structured manner. And then we define all the dynamic possible combinations of parameters, which is they can be car moving, people moving, animals moving, boxes moving. And all this ontology, we extended and we developed also with several OEMs. And this represents our basic, our basis for generation of test cases. This is a knowledge-based representation. So I'll try to increase it a little bit to see if I can make it a little bit bigger. Okay. So you see here, you have for the static part, a lot of information on this is just an example. So you have all these type of roads which are available. You will use later on to generate, and you will combine all this in a certain way. And this is the dynamic part. That's such a small example. What was also very important for us, and we took over the leadership of this project, it's the ASAM project, which is AVL List leading, where we also try to define for this ontology a standardization, so a structure which can be used by everybody. All Audi is also part of it, and the other companies, Toyota, it's also part of it. A lot of so it's an international assembly, where AVL has a leading role on this, and where we try to build up a standardized represent. So not with the information, of course, this is a propriety of the company, but try to agree on a structured way of approaching the levels. We defined levels and so on for the ontology, and we'll also look at other projects. This also helped us to go into another direction together, where also Audi or for Retelix is going, is trying to use ontologies as specification language for let's call it semi-natural language representation of requirements, where we can automatically generate test cases. So again, I will show you shortly about this. Okay, so you see here, the user can, if you're familiar with the Audi system, Steve, it's the same principle. The user can only specify some wordings, and they are in a relationship, those wordings, so they cannot just naturally write everything, but there is a natural language interpretation of it. That's why I'm calling it semi-natural. And behind this specification, like the lane width of the incoming roads is blah, blah, blah. The air vehicle, it's a truck, and so on and so forth. This has in the background an ontology. So also here, the ontology plays a big role in structuring and limiting the information which is available. This is also a use case where it's more requirements-based for generating test cases. So here I'm describing the different scenarios in the ontology in the background, which I will also use to generate test cases. How this looks like? Well, you have on one side the ontology, then you have this test case generation where you have the algorithms we developed by On, and we also patented that. And then we do an executable scenario generation. So basically we generate right now strongly in OpenX format, as I'm OpenX, because it's standardized and supported by most of the simulation tools. But we have also special requests for special simulation tools where we also can accommodate. And these scenarios can be directly executed and interpreted by the system. How do we perform against? So we made a lot of comparison for different functions to see how we will perform against different ways. So one way of doing things is for very simple parameters is try to work with full factorial, which is almost impossible. So full factorial, when you get into two parameters and so on, you already speak about years, days, and so on. So we test also for another number of parameters. We tested up to, for our algorithm, we worked up to 300 parameters, and then with larger domain values. But for full factorial, about 21 parameters, it's too much. So you cannot manage it. And it's a lot of redundancy in the full factorial, so you don't need all the test cases. And we also compare it with different random testing techniques, inclusive the one which is from Google, the fast one, Monte Carlo, of course, but there are also other random tests. We managed to hit, of course, everything being a parameter-driven comparison. We managed to hit everything in one run. There were necessary several runs, and with the other random-based techniques, there was not possible to cover all the space. And I think that's quite. With respect to the LM load matrix for software, it's called our algorithm, which is implemented here. You can see here all the times are quite, and the test suite is quite efficient. So we have really small test suites covering a lot of parameters. So if you know a little bit about the combinatorial part, you know that generally when it's generated, and this is also specific for our algorithm, when one test case is generated, one line is generated, then the focus is that one line covers as much combination as possible. And it's right now very, very efficient. We are trying also, there is one other algorithm which is coming from Japan, and we are trying also to compare with this and see if what we know, we manage for sure much more parameters. We want to see for lower number of parameters, even there we are faster. Okay, but the reality, it's a little bit of another one. The reality is that we have now several customer projects, and we have test suites which are million of test cases, and that's okay, because if we would have done it full factorial, it would have been 10 to the power of 12, so trillions of test cases. That's huge. Nobody can execute it. However, even million of test cases is not possible to execute on a single machine. So right now our approach is fully integrated in the cloud. We can work with different simulation environments like VTD or CarMaker, BNG, and so on. And we can also execute this in the cloud, and then have a fully integrated environment, either with VTD and with CarMaker. These are the ones. So, and we really then get really nice data. We have now a project where we have 100 instances of CarMaker, and there is an estimation that will run about 2 to 3 million test cases every 3 weeks, which is quite a nice number, including everything execution updates. So that's mostly on the execution part. Okay, the second approach, what I told you, so if we manage to cover everything over the parameters, and we are sure that we have everything in line, in place, we would like to play even more. We like to play even more against the system and try to see if we have we've missed something. This is what we. I think somebody can mute. Okay, so here what we do here is the system is trying to play. So here you see a corner case. The system is playing against it's an AEB function, and is combining different situations like a cut in and a double. So you see here the guy here is breaking, this one is cutting in, and so on. I was told this is not really an edge case because this is a popular scene in Munich. I also saw it in other countries. So but basically the system is searching for such kind of situation. It's playing and it's re-executing. It's learning every time, and he's trying to see what makes my function weak, and then how can I use it. And one example we had here, it's what I called corner case and edge case creation. So on one side, it's the AI algorithm behind it, but what we also try to do is, when we create several corner cases, is try to combine them. And also what's important, and we have a lot of customer, and this is blurry, not because the camera was a problem, but because of data protection in Europe, is to collect data from the street, normal data, like you see here. So I would show my mouse is again doing strange things. So like you see here, here it's a in-vehicle collected data, nothing dangerous. There is one little situation here, but not nothing specific. You have the Aussie stream here below, and then you convert this data. We have a converter which converts Aussie streams into OpenX, open scenario. Then we create out of this data corner cases, and then we can combine those corner cases here, like you see here, to create edge cases, we call. So edge cases are a combination of several corner cases. Like in this situation, the system had a braking, and then also thought about inserting a motorcycle between, and combining this, you get the edge cases. And all this is done, as I said, we are using search-based methods, where there are also some other AI-based algorithms behind it. We used to generate these kind of test cases. On my last slide, what I would like to say about this is that what we also, as I told you, we applied these methods for starting with a meal environment, so the model in the loop, so simulation, purely simulation. Then we tested on the heel, so on the hardware in the loop, and then I had a look on how the system behaves when combined. There were very similar results. So here there was a huge number of test cases, cloud computing and so on. Here there were some special set test cases selected, and then we moved into vehicle in the loop. So what we have the AVL driving cube, where we have the full environment simulated. Then we have radar emulator stimulators. We have camera stimulators. We are also working into investigating LiDAR simulators as possible, but right now for LiDAR we are doing in-vehicle insertion. So we are integrating this directly on the vehicle CAN, the data. And then we did the same tests on the real world. And there was because these tests were very similar. What we did, we had a testing track here when there was an NCAP testing scenarios, and we need about a week here, and I would say 6 to 8 times the costs we had here on the vehicle in the loop. And here we had about 5 hours executing the same tests, and we compared the results, and we are like 4 to 5% difference on the results. So it was quite efficient to do the vehicle in the loop testing part. But what is important is that the method can be used generally from simulation up to the real world. As I said, what we have a method to always filter and reduce test cases based on the test execution results and decide which test cases are carry over for the next phase of the execution. So this is shortly about how AVL is doing, and my team is leading these things in AVL on generating autonomous or generating test cases for testing autonomous driving systems. Yeah, thank you very much for your attention. I hope I have stayed in time. If you have any questions now, please ask. If not, you have my email address here. I think it will be also in the proceedings, so you can also drop me an email, and I can also answer this email. So yeah.
Let me ask one question first. Yeah, so hi Mihai. So you mentioned that you have your hardware in the loop and the vehicle in the loop looks very interesting. And you talk lots about the generated simulation, about some of the scenarios. But how these general scenarios can be used to test for hardware in the loop or even vehicle in the loop?
Yes, so basically what we do an execution on the simulation. Then we look at we share the test cases into confident, let's say, so we know that it will fail or it will pass. And then we based on the KPI evaluations on the test oracle on the final execution, we call it what we call the yellow area, where we are not sure about. And for this, let's say we are executing 2 million of test cases in the cloud. And there is an amount of tests they don't have to be in linear, so they can be distributed, where we have a certain uncertainty because of the way the execution was KPI was evaluated. And what we do, we take these test cases, and there are also special homologation tests where you have to do the vehicle test, so you cannot come around. And we take this test cases and we say, okay, for these test cases, we move towards the next environment, and we argue then to the homologation or to the legislation body. For the other test cases, we had the simulation results, and because of that and that and that, we are sure there is no failing. There shouldn't be no failing on the upper areas. And there are some other ways of, to some extent, also, of course, available to customers, but we keep it confidential. Sorry, confidential. Yeah. So, but the basic idea is based on the test execution of one phase, we are moving towards the next phase and reducing the subset.
Okay, thank you. Yeah, so I saw in the vehicle in the loop testing, you put a huge screen in front of the vehicle to
for the camera
the real world.
Yes.
Okay, but does like a millimeter wave radar and the LiDAR can also be included in the
yes, there is we have a special partnership with a company. You probably saw it, but yeah, we have radar stimulators. We have special, so radar and camera. We have it for LiDAR. We tried several things. We are also working with some company trying, but it's very hard because you have to do every channel you have to, and there are people doing this, but right now we're doing just directly on the vehicle, so we are not really stimulating the LiDAR part, but there are companies which are dealing with this, and there are some tries, but as far as I know, nobody really managed to do it. So yeah.
Okay, thank you. Okay, any other question from other audience? Okay, if no questions, that's concluded the session. Thank you.
Thank you very much.
Thank you.